Hello and welcome to our webinar. I'm Jennifer Gottwald, Director of Licensing at WARF, the Tech Transfer Office for the University of Wisconsin-Madison. We're really excited you could join us today to hear about understanding the global plastics problem to inform solutions. We've got an amazing speaker today, and I will get to her in just a moment. So first, I want to explain a little bit about the WARF Searchlight project. This is a new project that WARF initiated in 2022, where we are scanning the horizon for the technologies of the future. We get amazing inventions from the University of Wisconsin-Madison, and we're looking at what business needs are going to be out there, technological needs in business that we're not even thinking about consciously yet. Get ahead of the curve and spend some time informing ourselves about who might be working on relevant research on campus, building our networks within the industry, and finding out what their needs are. One of our Searchlight projects this year was on plastics recycling and composting. And one of the results of that project is this webinar you're going to hear today. I want to invite you, if you have ideas for what our Searchlight project should be for 2023, please reach out to me, jennifer@warf.org. During the talk today, we're going to ask you to put your questions into the Q&A feature of Zoom, and we will moderate those and look for those and have a chance to answer them at the end. But right now, I want to introduce Professor George Huber. He's the Richard L. Antoine Professor of Chemical Engineering at UW-Madison, and his research is focused on developing new catalytic processes for the production of renewable liquid fuels and chemicals. I've been able to work with George and his technology since he came back to UW-Madison some years ago, and it's been a real honor and a privilege to be able to do so. His technology is in at least 3 startups. He's a founder of 2. And he's got great industry connections too. And I know he's always looking for the practical applications of his research and how to make a difference in the world. One example of that, of his great convening power, is the 2020 award from the Department of Energy of a $10 million multi-university grant on the chemical upcycling of plastic waste called Cup Affectionately. So with that, George, I'm going to ask you to introduce our speaker.
Thank you, Jennifer. It's an honor to introduce Dr. Kara Lavender Law, who is a research professor of oceanography at Sea Education Association in Woods Hole, Massachusetts. She studies the sources, distribution, transformation, and fate of plastic debris in the ocean. She's trained as a physical oceanographer and has more than 12 months of sea time in oceanographic and sailing research vessels. Her research interests include the sources of plastic debris to the marine environment, understanding how ocean physics determine the distribution of plastics and other marine debris, and the degradation and ultimate fate of different plastic materials in the ocean. She's served as co-principal investigator as the Marine Debris Working Group at the National Center for Ecological Analysis and Synthesis, is co-chair at the SCOR Working Group Flotsam, Floating Litter and its Oceanic Transport Analysis and Modeling, and served on the U.S. National Academy of Science, Engineering, and Medicine Committee that published the report Reckoning with the U.S. Role in Global Ocean Plastic Waste in 2022. I highly recommend you read her report that she wrote on Reckoning with the U.S. Role in Global Ocean Plastics if you're interested in the topic. She holds a PhD in Physical Oceanography from Scripps Institute of Oceanography and a BS in Mathematics from Duke University. So please join me and welcome Dr. Law.
Well, thank you so much, George and Jennifer and WARF, for having me here this afternoon. Thanks to all of you taking time on what I hope is as beautiful an afternoon where you are as it is here where I am in Maine. I'm going to go ahead and share my screen, and then we can get started. Okay, hopefully everybody is seeing that title slide. So yes, again, I'm really grateful to have this invitation to speak to you all today about this important issue, what I think is now pretty widely known as the plastics problem. And what I'll be doing today is sharing my perspective as an oceanographer who's been working on this issue for more than 15 years now. But of course, the global plastics problem is much more than just an ocean problem. And I'm going to argue here today that without the ocean focus, I think we might not yet be taking seriously the complex situation that we've collectively created as a society with plastics. So as I'm sure you all know, more than 70 years of innovation in this really exceptional class of materials has brought unprecedented societal advancement, and with it, really a reliance on plastics. We all rely on these materials in everything we do pretty much all day, every day. But this has come at a cost that we're really only now beginning seriously to address. And so the story I want to tell today begins with that environmental cost at what I call sort of the end of the pipe. And that is from the middle of the open ocean. And that's where my work on this topic began. So just to give you a sense of where we're going this afternoon, I want to spend probably most of the time talking about what we actually know about the scale and the scope of the plastic pollution problem, largely from the ocean context, but expanding into different parts of the environment. And I'll include a bit of historical context there too. And then I want to spend the latter part of the talk to present some food for thought on potential approaches to addressing global plastic pollution with the goal of achieving sustainable outcomes. And by sustainable, I'm referring collectively to environmental, economic, and societal outcomes, recognizing that when we try to optimize one of these three pillars of sustainability, that often comes with costs in another. There's no free lunch. Okay, so I want to begin first with a curve that I'm sure most people have seen in one form or another, and that's this blue curve here, which is a curve of global plastic production in units of million metric tons. Let me get a pointer. Let's see if I can do that, laser pointer. Okay, there we go. So this is units of million metric tons as a function of time, since what we now collectively think of as the nominal start of the commercial production of plastics in 1950. Really, this is when we first started tracking the global production of plastics. So what you can see by the blue curve is that plastics production experienced rapid growth nearly from the start. And especially in recent decades, the growth in plastics production has outpaced that of all other bulk materials, including things like steel, cement, and aluminum. And global plastics production has actually more than doubled since the year 2000. Well, this growth really reflects the nature of this class of materials that are now essential to modern society. And that's because of their properties. The properties of synthetic polymers include things like they're lightweight, they're durable, have high strength, and chemical resistance. And these properties are combined with a breadth of chemical additives that really allow for what seems like limitless versatility for both short-term applications like single use and long-term or durable applications. So in work led by Roland Geyer at University of California, Santa Barbara, we integrated this production curve, that blue curve again, and we found that since 1950, more than 8.3 billion metric tons of plastics have been produced. And that number is so big that I can't translate it in terms of elephants or Olympic-sized swimming pools or anything like that. It's still not meaningful. It's such a huge, huge number. Now, what you also see on this plot is a curve of plastic waste generation. That's the red curve on the same time scale and on the same scale on the y-axis. And what you see is that curve is essentially the same shape, but it is just slightly offset. And that's because while most plastics do become waste in the year that they are produced, the durable goods have lifetimes that are sometimes many years before becoming waste. So that's why you see that offset. So in this work, we found that 70% of plastics that have been produced since 1950 have become waste. And of that, only 9% of that waste has been recycled and 12% has been incinerated. So what that means is the vast majority of that waste is residing in landfills or somewhere in the environment. And when we take that waste and look at it together with plastics that are still in use, this means that an estimated 90% of that 8.3 billion metric tons are still in existence on the planet. So we often hear the term plastic used as if it were a single material, whereas instead plastics are actually a material class consisting of hundreds or maybe thousands of distinct polymers that again are further diversified by chemical additives. But when we break down that curve of global plastics production, so here the green line is that same curve that I showed you just a second ago that was blue in the previous slide. If we break that down into polymer specific contributions, what we find is that the majority, nearly 77% of the plastics that we've produced to date have a common chemical structure that consists of a carbon-carbon backbone. And so you can see that illustrated here. The carbon-carbon backbone plastics are shown in the sort of darker blue curve. Now, as I'm sure many of you know, having chemistry backgrounds, the carbon-carbon backbone is important to the defining properties of plastics that I mentioned earlier, but it also renders these materials strongly resistant to biodegradation. So from a material or a product application perspective, this is actually really important and typically a desirable characteristic. But the resistance to biodegradation also means that these materials are persistent if they are lost to the natural environment. So they are persistent in the environment, but they're not stable in their composition. We know that when plastics are exposed to sunlight, photochemical degradation occurs, and this causes a reduction in the strength of the material and renders them susceptible to breaking or fragmenting, ultimately causing fragmentation into particles perhaps as small as nanometers in size. And I'll come back to this point a bit later. But using this curve, I want to make one last point, and that's that packaging, shown as that other blue curve, actually accounts for nearly 45% of global plastics demand by application. And the majority of that materials used in packaging are also composed of these carbon-carbon backbone polymers. So as we all know, packaging readily becomes waste, and that in part explains this cumulative waste generation curve that you see on the right-hand side that is predicted to accelerate, that's those dashed lines, as we continue in coming decades, predictably, to increase production of those same carbon-carbon backbone commodity polymers. And then finally, the red curve here, this plastics accumulation curve, really is just reflecting the minimal amount of removal of these synthetic materials from the planet over time, and really only through combustion or incineration, burning them. Okay, so I'd now like to use the same timeline to look at the historical evolution of our knowledge of plastics in the marine environment. So we finally get to the ocean. The first evidence of plastics contamination in the oceans was in 1966, when researchers identified out of 100 Laysan albatross chick carcasses in the Northwest Hawaiian Islands, they found that 74 of those already contained plastic in their guts. And you can't really see this photo very well, but it is a black and white image of a seabird carcass with bits of plastic. So this is because the adult parent albatross forage in the open ocean and collected plastics and fed those to their chicks. So this report in 1966 was when global plastics production was just 5% of current production levels. The first reports of small bits of plastic floating in the North Atlantic and the North Pacific Oceans was in the early 1970s. And it was also in this time when larger, more recognizable objects were documented far offshore in the North Pacific, including things like flip-flops. And this was in the 70s, when plastics production was only 10% of current production levels. My organization, Sea Education Association, or SEA, first started researching floating microplastics in the mid-1980s, and I'll tell you a bit more about that in a moment. So our students and scientists have been thinking about this for many decades, but I would argue that it wasn't until the 2000s, until 2003, in fact, that people really started paying attention to plastics in the ocean. And that was when a man named Charles Moore, who's a very avid sailor and environmentalist, wrote an article in Natural History magazine describing his view of the North Pacific Ocean from the deck of his ship as, quote, "as far as the eye could see, the sight of plastic." And it was in this article that the term garbage patch was born. So although plastics production has always been on a strong growth trajectory, and scientists have been documenting contamination in the oceans and in marine wildlife for decades, no one was talking very much about plastic in the ocean until the garbage patch entered public consciousness. Well, soon after its birth in the early 2000s, the garbage patch developed into sort of a phenomenon. It was described as twice the size of Texas or 3 times the size of France and having more plastic than plankton, and was also described as being a floating island visible from space. So let's just clear that up. Although this is a very striking and very memorable portrayal of the garbage patch, there is no floating island visible from space. And here's my data to support that. This is actually an image taken by a friend from graduate school who is now an NASA astronaut, Megan MacArthur, who flew on the International Space Station last year and asked if I wanted any photographs of particular parts of the globe. And I said, yes, please take a photo of the garbage patch in the North Pacific. So there's actually no way for you to know that this is the Eastern North Pacific Ocean. You'll have to take my word for it. But this is the view of that part of the world about 250 miles up. And it took them actually quite a while to get a photo without clouds so that you could see the ocean surface. And obviously there's no floating island there. Well, let's bring it back to Earth and talk about what I've actually seen myself. So this is a photo taken from the deck of one of our ships at SEA in the garbage patch. So what you typically see when you're sailing in the subtropical latitudes of the North Atlantic or of the North Pacific, you typically see on a nice calm day, really nothing but water, clouds, water, sky, clouds, really very few ships. You might be lucky enough to spot some wildlife, some dolphins or albatross or flying fish. But you will see floating debris items drifting by. And these can actually be as frequently as one item per minute if you're looking over the side of the ship. But they're typically singular items. Sometimes they're identifiable. So this is actually a boot floating upside down. Here we have a 5-gallon bucket, a tire that we collected that was drifting by. More often than not, though, these are just fragments or chunks or pieces of items that you really don't know the origin of. So you can see in examples of some of those types of things up here in the upper right image, and this kind of plastic film that got pulled aboard down here. So some of these photos, including everything in this bin and this tire, were actually items that we are quite sure originated from the Japanese earthquake and tsunami in 2011. That delivered millions of tons of debris to the other side of the Pacific Ocean. These images were from about 18 months after that tsunami. So it was an incredible human tragedy, but also a kind of an interesting oceanographic experiment to see these objects that had drifted across the ocean, including a floating refrigerator with some of these food packaging items inside of it that we identified from our ship. And then there are also very large items. This is actually a picture of what is likely a derelict fishing gear or possibly a fish aggregation device that's used for fishing to collect fish, or to fish are sort of attracted to them underneath for fishermen. So if you're an open ocean sailor or somebody who has been out in the open ocean a lot for research, for example, seeing these kinds of items hundreds or even thousands of kilometers from land is at first surprising and even kind of thrilling, like, oh my gosh, what is that tea kettle or toothbrush or children's toy doing drifting by? And then it's shocking, and then you're really kind of depressed because trash obviously doesn't belong in the ocean. But the picture changes quite a bit when you measure what's floating at the sea surface by towing a plankton net through the water for 30 minutes and sifting through its contents. And what I'm showing you here is a picture of a plankton net that our students at SEA in our undergraduate sea semester program have been towing for decades. So just briefly, for those who aren't familiar with SEA or sea semester, we are a sort of study abroad program where students come to us from colleges and universities across the country and also from abroad. And they spend a semester with us, half of which is on our campus in Woods Hole, Massachusetts on Cape Cod, preparing to go out to sea and to conduct their own independent research on board our tall ships sailing oceanographic research vessels like you see here. So we have one ship that operates in the Atlantic and the Caribbean and one that operates in the North and Pacific Oceans. So these students design research projects that they carry out on board the ship when they are active crew members, also participating in the ship's navigation and sail handling, working in the engine room, working in the galley, and working and standing watch in our oceanographic lab. This plankton net, which we call the Newston net, is a real workhorse. We have towed this net for decades. SEA has been around since 1971, collecting plankton and other types of data for our student research. So we've towed this net twice a day, every day for 30 minutes. It's a meter wide and half a meter tall, and the mesh is about a third of a millimeter, 0.335 micron, or 335 microns in size. So we tow this net for 30 minutes and we bring the collection jar aboard and pour it into a sieve. And this is what you see in a very highly concentrated sample. So among the plankton are bits of plastics, which we now refer to as microplastics. And what you can see from this photo is that most of these particles are really pretty easily distinguishable from organic matter. So there are some sort of jelly and brownish blobs in this sieve, but most of what you're seeing are these plastics. And you can tell that because of their bright colors and their irregular shapes, and they're typically hard texture if you pick them up with some tweezers. Well, it turns out from some laboratory work that we've done after the fact that we can confirm that the human eye and the human brain does a really excellent job identifying plastics from organic matter at the sizes collected in our plankton nets, so larger than about 0.5 millimeter. And that's verified using Raman spectroscopy. Well, I want to take a minute and talk about what are microplastics. We hear an awful lot about microplastics now in just the media and in academia. In fact, I would say, in the time that I've worked on this, the conversation has largely shifted from garbage patches to microplastics. So I'd like to spend a moment talking about what they are. So what is the technical scientific definition of a microplastic? It is a small bit of plastic. There's not actually a strict scientific definition in existence at this point, and there is a reason for that. So first, originally these were defined by size. And that early definition really reflected the method of observation in the ocean. And that is really what I just talked about, using plankton nets with a particular mesh size. So microplastics were initially described as 5 millimeters in size or less. So 5 millimeters actually captures industrial resin pellets, which I'll show you in just a second. And so originally people were measuring microplastics down to about 0.5 millimeter, 1/3 of a millimeter in size. But over time, we've used finer mesh on nets, and we've also just used bulk water samples on really fine mesh. And it turns out that the smaller the particles we can detect, the smaller particles we find. And that's perhaps down to nanoscales. So microplastics are still typically defined by their size, but I will say that these definitions vary widely. So you should always read carefully if somebody's writing a paper about microplastics. Microplastics are also commonly described by their shape, and some of those shape categories include pellets. So I told you about mentioned the industrial resin pellets. So you can see here a couple of examples from our plankton net tows of industrial resin pellets, the sort of raw material of plastic products. We also have line, and here this is not textile fiber. This is most likely fishing line or line that was shed off of fishing nets because it's quite a bit thicker than a textile fiber. Then we also have film, which is a little hard to see. There's one little piece of film here, super thin. And most of what we collect is fragments. So fragments of items that were once larger in size. And so part of the reason that we describe these particles by their shape is because it gives us some indication of their source. So some microplastics are actually manufactured in this size, things like microbeads that have been used in cosmetics, or industrial resin pellets are primary microplastics, or plastics that are used as abrasives or industrial scrubbers. But most of what you see in the photo here are formed from fragmentation of larger objects. So as I mentioned, sunlight weakens material, and then these physical shear and straining forces cause it to break into smaller and smaller fragments that are often referred to as secondary microplastics. And their origin really can almost never be determined from the particles themselves. And by origin, I mean either where they came from geographically or the type of object. There are other types of microplastics that are shed during the regular use of an item. So those are things like textile fibers, but also things like particles from tires. When you apply the brakes, those particles are shed from tires. I don't have any photos of that here. So microplastics are also described by polymer types. So you're familiar with these resin codes or recycling codes that are stamped on the bottom of many of our everyday products. And each number refers to a specific polymer type. But even with specific polymer types, a number 2 milk jug is not chemically the same as a number 2 detergent bottle. And that's because of chemical additives, which are proprietary formulations that give products their color or enhanced properties such as flexibility or stabilization against that UV light or antimicrobial properties, for example. So when we think about all of these ways that we describe microplastics, what this comes down to is that microplastics are really a very diverse and a complex category of contaminants. And it's further complicated by the fact that their characteristics evolve when they're exposed in the environment. So plastics become smaller, they change their shape, and their chemistry can change. Well, in the 15 years or so since I've been working on ocean plastics, it's become readily apparent that microplastics are the most numerically abundant form of plastic in the marine environment, and also the most widespread type of plastic debris. So what you're seeing here are just a few images from different sort of compartments of the marine environment. This is from Camilo Beach on the big island of Hawaii, and you can see these microplastics are quite dominant in the black sand. Another photo of microplastics collected with a plankton net tow at SEA. And then you see these photos of microplastics that were found buried in deep sea sediments in the North Atlantic, Mediterranean Sea, and South Atlantic Ocean. And even images of microplastics that were frozen into sea ice in the Arctic. And here in this case, you can see these fibers that may have been derived from textiles. So we've also learned since the time I've been working on this that microplastics are not only in the marine environment, they're also in freshwater environments like lakes, streams, and rivers, in the terrestrial environment, including agricultural and other soils. They're in the air, they're in snow, they've been found in rain falling on national parks, in drinking water, bottled water, wastewater, stormwater. It seems that the smaller part the particle is, the more abundant and widespread they are, and especially those microfibers. And that's perhaps because they can be readily transported not only in water, but also in the air. So what I'm showing here is a compilation of some work published by Janice Brani at Utah State. She published these two studies. First was the science paper was examining microplastics in wet and dry deposition samples in US national parks. And what she found was that 2 to 6% of the particulate aerosols that she measured were composed of plastics. She then led a follow-up study doing some modeling to assess the likely sources of these microplastics to the atmosphere, which you see on the sort of cartoon on the left. But really what I want you to focus on is this model estimate of microplastic deposition, where the reds are the highest values and the blues are the lowest. And what this global map demonstrates is that deposition of microplastics is not equal everywhere. You see it's much higher in the subtropics than in the tropics or the polar regions. And that's going to do with having to do with atmospheric physics, at least in part. So let's turn back to the ocean and look at the distribution of the floating microplastics that we've collected at SEA for decades with that plankton net that I showed you earlier. So what you're seeing here is a map of the Western North Atlantic Ocean. So we have North America, here's Cuba, Haiti, Dominican Republic, South America, here's the Caribbean Sea. And on the right, we have the Eastern Pacific Ocean. So here we have the US, the sort of concentration of points here is in Hawaii. Then we have Tahiti at the bottom and Puerto Vallarta, Mexico, just to orient you. So in each of these maps, you see many, many dots, and each dot is representative of the location of one plankton net tow. And the color is telling you the concentration of plastics measured by counting those pieces in the sieve and dividing by the area, the surface area of the ocean that was sampled. So that's units of pieces per square kilometer. So the color scales are a little bit different between the two, but generally reds and pinks are very high concentrations and black. And the darkest blue is actually 0 plastics that were measured. So what you can see is, and in the Atlantic also, the stars are indicating the very highest concentrations that were measured. So the first thing you'll see is that the highest concentrations, those black stars, are really the warmest values, are found offshore, which might be a bit surprising given that most of the plastics that we use, and certainly all the plastics that we make, come from or originate on land. In both the North Atlantic and in the Eastern North Pacific, you'll see if you sort of squint that this collection of the highest concentrations, the reds and oranges and yellows, is centered on a latitude of 30 degrees north and spans from about 20 or 25 degrees north to say 40 or 45 degrees north. So the reason that we have these very high concentrations of plastics in that latitude range can be explained very well by ocean physics. So the winds blow on the surface of the ocean, and that combined with the turning of the earth or the Coriolis effect creates ocean currents that form gyres, which are large circulating current systems that really span entire ocean basins. I can't even show you the whole span of the gyre because I don't have the full ocean basin mapped in either case here. But in the center of the subtropical gyres, the currents come together and slow in what are called convergence zones. And so anything that's floating at the sea surface is carried with those ocean currents and sort of collects and comes to a stop. I like to think of it as sort of the dead end of the ocean surface. So what you can see is that the highest concentrations are centered in these regions. This is really what the garbage patches are. This is a high concentration of plastics in a very particular region of the ocean, although it's not so much big floating islands, and instead it's these little confetti-like pieces of plastic that are swirling about. I like showing the Pacific map because you can really see that outside of the garbage patch in the tropics, we find very little plastics. And in fact, the ocean currents along the equator and in the tropic region are divergent, so they carry material away. So even if you sprinkled microplastics along the equator, they wouldn't be there for very long because of ocean circulation. One other thing I want to point out from these maps is that even in the high concentration region, it's a little hard to tell because of the way we plotted this, with the lowest concentrations plotted first and the highest concentrations on the top. But over here, for example, you can see that there's extremely large variability even between 2 sequential tows that might be only 4 hours apart. So in this case, you can see one of the highest concentrations we've ever measured right next to one of the lower concentrations. So there's extremely high variation, and even some tows where we collect no plastics in those garbage patches. So for this particular data set, for particles of this size, which again is about larger than about 1/3 of a millimeter, ocean currents in these basin scale ocean gyres really largely determine the accumulation pattern. Now I'm showing you a different map here showing, again, the distribution of microplastics in the environment. And this comes from a citizen scientist initiative led by a group called Adventure Scientists. In this initiative, they had volunteers across the globe collecting 1 liter bottle samples of water from both marine and freshwater environments. So just like this Nalgene bottle. And then they sent them into Abby Barrows, who spent countless hours of her life filtering these with a very fine filter. It's 0.45 microns, and then counting the microplastics that were measured in those 1 liter samples. So just for comparison's sake to what we're doing with our plankton nets, the smallest particle that could theoretically be measured by this method is about 750 times smaller than the smallest particles collected in a typical plankton net. So really, we're measuring a very different thing with a very different volume of water. So 1 liter of water versus about 2,000 bathtubs of water for a single sample. The map is somewhat similar in the sense that each dot represents a single sample. The larger the bubble, the larger the measured concentration of microplastics, and the yellow bubbles are showing you places where 0 microplastics were collected. So what I just want to point out is that in this map, it's really not so straightforward to identify a pattern in the way that we identified the pattern from the previous data set I showed you. There are very high values spanning lots of different regions, including high latitude, low latitude. There are zeros distributed throughout. So you can see that, again, there's very, very high variation, and the accumulation patterns are different because we're looking at a different type of microplastic. So comparing that previous slide and this one, there are a couple things to remember. One, a microplastic is not a microplastic is not a microplastic, even if you're not thinking about polymer type and what kind of additives it has, just because how we measure matters. There's a large variation in particle size. But also microplastics are globally distributed, but they're not everywhere in the same amounts. Okay, well, naturally faced with this widespread global contamination, environmental scientists really want to understand the impacts on biota and ecosystems by microplastics. And that really continues to be a major focus of the research field. Now, this is a little bit of a complex picture, but I think it's worth talking through. This is a 2019 study out of Chelsea Rockman's group at University of Toronto. And it was a critical review and meta-analysis of all of the scientific evidence published in the literature on the impacts of plastic debris, ranging in size from nanometers to kilometers in scale. And this was looking at effects in marine, freshwater, and terrestrial ecosystems. So what you see plotted twice here are these grids plotting on the x-axis the size of debris from small to large, and then the impact that was studied in a particular study, starting from ecosystem all the way down to organism level, and then suborganismal effects, including on organ systems, tissues, molecular assemblages, atoms, etc. I am not a biologist, I'm not an ecologist, so don't ask me to explain what the subatomic particle effects were. But the point of this is that what they did was they shaded each box for a particular biological level of organization and a particular size of debris according to what the study was testing, and then whether or not they found the effect they were testing for. So on the left, and I should say also this red line here is roughly indicating the boundary between microplastics, which will sit to the left of the line, and macroplastics, which will sit to the right of the line. And the darker the square, then the larger the number of effects in that particular graphic. So when they looked at, for microplastics only, the number of studies that tested an effect and detected it, they found that out of the 421 effects tested across all these levels of biological organization, about half found an effect and about half tested for the effect but did not detect it. So this suggests that there certainly is reason for concern. There is evidence of biological impacts due to microplastics all along these different levels of biological organization. However, we can't yet, or maybe ever, make really sweeping generalizations about the risk or harm to animals or ecosystems, because in the other half of studies, they found no effects. So not only was there variation in whether a particular effect was detected, but by and large, these studies all occurred in controlled laboratory settings using one or maybe a few polymer types and probably one type of organism. Whereas in the environment, exposures are likely to be to very complex mixtures of materials. Their concentrations are highly variable, as I showed you in the previous slides. And in most places, what particular animals or groups of animals are even exposed to is largely unknown. Well, I want to point your attention to the right-hand side of this slide, where we look at the effects of larger debris. And in this case, you'll see actually that most effects were tested for and detected. There's not very many shaded boxes on the no effect side of that plot. Well, this is indicating that there's much stronger evidence of harm to tissues, individuals, because most of these effects were up at those higher levels of biological organization, populations, and even ecosystems due to large plastic debris. And this shouldn't be surprising, because we've all seen these impacts over and over again in images like this one that really evoke quite visceral reactions to ocean plastics. So here we've got an albatross chick, a modern day albatross chick with bottle caps and a cigarette lighter in its gut. And lots of other impacts, sort of gut-wrenching images that you'll see here for a couple minutes. So earlier I suggested that without an ocean focus, we might not yet be discussing new solutions to accelerate things like plastics recycling or material redesign. And the first pillar of that assertion was this public perception and disgust of this notion of a garbage patch in the middle of the ocean. But I think the second pillar to that argument is images like these, especially these modern day poster children of the albatross chick and this olive ridley sea turtle who had a nasty encounter with a plastic straw, that really stick with us and stick with the public in finding this unacceptable. So it's really hard to ignore these kinds of images. Well, this is beyond these risks and impacts to marine wildlife. We also now are starting to talk about potential impacts to humans, specifically from microplastics and potentially also from even smaller nanoplastics. We are finding every day a wealth of studies that are documenting microplastics in items that we humans consume. So things like seafood and bottled water, tap water, sea salt, beer, honey, tea, and even fruits and vegetables. And in fact, a new report was just released from the FAO assessing our knowledge on microplastics in food. So I encourage folks who are interested to look that up. Well, it's one thing to find microplastics contaminating our food and our drink, but are they actually in our bodies? And now we're finding really kind of rapid fire medical studies that indicate that yes, there is exposure and transmission in the human body. First, microplastics were detected in human stool, then in the placenta, then in lung tissue, in human blood, most recently in breast milk. Well, this raises the obvious question, are these microplastics causing harm either to the marine wildlife or to humans? And this is where it becomes really important to distinguish between contamination and impact and what we know and what we don't yet know. So the majority of scientific studies currently document the contamination of biota by plastic debris. So that's by that I mean plastic debris interacting with an organism through entanglement or ingestion or in other ways. And in some cases, that contamination, here we go, has a clear negative impact on the animal, like this sea lion that was rescued by the Marine Mammal Center in Sausalito that had this plastic packing band around its neck, clearly causing injury. The good news is the sea lion was rehabilitated and released back to the wild. So that's a case where contamination clearly has an impact. But in the case of microplastic ingestion in particular, we often don't know the short or the long-term impacts on wildlife or on humans. I do think that we can all expect to hear a lot more on this in coming months, years, as toxicology research, especially specific to human ingestion and inhalation of microplastics, is now really ramping up. And also because of this concern about human health, I think it's safe to say this attention to the plastics problem is not going to go away and is really likely to intensify. Okay, so before I go on to the solutions part, I want to just quickly summarize sort of the path that we've traveled so far. What do we actually know about the plastics problem? First, billions of metric tons of plastics exist on the planet, and we can pretty safely say this number will continue to grow and it will likely accelerate. Most plastics to date with carbon-carbon backbones are strongly resistant to biodegradation, therefore they are persistent in the environment. I spent quite a bit of time trying to convince you that plastic debris and especially microplastics are widespread, but they're not uniform across the globe. And that plastic debris does span many orders of magnitude in size, possibly nanometers up to hundreds of meters or kilometers in size. And there is evidence that plastic debris clearly harms wildlife. Okay, well, what do we sort of know? I haven't had time to discuss in detail the plastic input to the environment, including the ocean. But I can tell you that a number of studies have now estimated this to be on the order of tens of millions of metric tons of plastic debris entering ecosystems, the natural environment, annually. It's important to know this is an order of magnitude estimate. It's a sort of ballpark estimate based on modeling studies that have relatively few direct measurements. And that's because direct measurements of fluxes of plastics to the atmosphere or to water or to soil are very sparse and they're highly variable for all sizes of debris. So what that means is that, well, we know that plastics are readily transported by air and water, and that they're transformed upon exposure to sunlight, heat, and oxygen. But the timescales of persistence and the ultimate fate of plastic in the environment aren't known because the fragmentation rates and those mechanisms are quite poorly constrained, as is the resulting particle size distribution. So when we ask how long is it there or what eventually happens, we really don't know the answer yet. Third, contamination of biota, including humans, by microplastics is widespread, but those risk assessments really are just underway, really in their infancy. So it's difficult to quantify or even qualitatively determine what the scale and the scope of these impacts are due to plastics in the natural environment. Okay, well, that said, even with these knowledge gaps, we do know, I would argue, more than enough now from an environmental perspective to take action. So with that, we're going to move to the solutions piece. So I've really focused on only one aspect of the global problem. That's the threat to environmental and a little bit of human health. There are others, including impacts of plastics manufacture, use, and disposal on carbon, energy, economics, and environmental justice. I just simply don't have time to discuss. But I do want to talk about how this global problem can be addressed. So what I'm proposing from the perspective of an environmental scientist is that the proximate solution, and by which I mean the closest or the most immediate solution to address the threat, is simply to prevent plastics from entering ecosystems, biota, or humans. So to sort of make this point, I'm showing here one of many frameworks that have been proposed to prevent plastics from leaking to the environment. And this one was actually put forth by that National Academies Committee that George mentioned earlier that I was very fortunate to serve on. And this presents interventions beginning at the production phase of plastics, stepping all the way through the pathway to design, use, disposal, and loss to the environment. So I want to take a couple minutes just to talk through some of these sort of colorful buckets that you see on this path here. So I do think, just before I start, that it's the reality is that all of us, from consumers to producers to policymakers, really have to take many different actions simultaneously to be able to properly manage the accelerating amount of plastic waste that we are generating. Okay, so let's start with production. How can we stop plastic from entering the environment? Well, what if we make less of it? So, you know, that's all well and good to say, let's just reduce plastic production, but how do you make that happen? And I think really to make that happen will require government actions to either cap or reduce virgin plastic production. And whether there's a political appetite for that is a completely different question. But aside from just looking at virgin plastic production as a whole, there have been actions that have been taken already at lots of different levels. Things like banning specific items like single-use plastic grocery bags, or in some communities, straws or polystyrene food containers. The US Congress actually in 2016 banned microplastics in cosmetics and rinse-off cosmetics. So you can ban sort of very specific items that you feel that is sort of acceptable. The government can also put incentives or disincentives out there on producers to make less plastic or on consumers to use less plastic. And that brings up the next piece of stakeholder engagement here, which would be consumer actions to reduce consumption. And if we use less plastic, then the demand for plastic should go down. So we can all do our part by refusing products that we either think we don't need, or we don't like how they're packaged, or we can find a replacement. We can all reuse and repair and extend those product lifetimes so that we simply consume less. Okay, if we go to probably the piece that might be of most interest to many of you in the audience, the innovation in materials and product design. So I think that material scientists and product designers actually have a tremendous role to play in this, because if we are going to make less things or try to innovate our way out, we're going to need to have new materials, new ways of doing things. So in a paper with Ramani Narayan published last year, we argued that material scientists and product designers should simultaneously design not only for performance, but also for end-of-life management, with the goal to strive towards circularity. I do want to say at this point that a lot of people really, really want the sort of magical, universally biodegradable material to be invented so that we don't really have to worry about this problem of things ending up in the environment. But we argue in this paper that the natural environment is really not a viable waste treatment system. And while there may be a role for biodegradability in very specific applications, it can't really be the universal solution. So we could talk more about that. Instead, the design for end of life really entails understanding the existing waste collection and waste treatment systems that we have today, and perhaps also working with those who are developing new waste treatment processes. And we really want to strive towards maximum recovery of materials over the maximum number of life cycles. That's really the cornerstone of zero waste and circularity. I think also in designing materials, we really need to put some consideration towards evaluating and minimizing the negative impacts if those materials happen to be lost to the environment. It's not just about new materials, it might also be about new ways of doing things, maybe innovating product delivery systems to minimize packaging, for example. There are also government actions here that can be taken. First, invest and incentivize in this R&D and assessment and scale up of these new materials or products. But also working sort of within the system by maybe instituting minimum recycled content standards in materials, or trying to disincentivize non-recyclable material use in products. That's commonly the philosophy behind extended producer responsibility. Okay, skipping down to waste management. I do want to say this is sort of a US focus here, where we have some of the best developed waste management infrastructure in the world. In the developing world, the task is much larger and much more basic, starting really with waste collection. But in the US, we still have work to do. We could expand and improve access to collection for recycling. There's also incentivizing collection through container deposit laws or bottle bills. I think it's critically important that we really understand what we're talking about. To be able to improve data collection and reporting on waste, because that's very decentralized in the US. We don't have a great idea of how much waste is being produced and what happens to it. And again, it's investing in innovative recycling processes. So again, that R&D assessment and scale up. And this is where the environmental and chemical engineers come in to hopefully be able to improve some of the existing waste processing systems, but also develop and critically evaluate the potential for new recycling processes for plastics. Okay, last thing I want to mention is the capturing of waste. So even if we do all of the previous steps really, really well, I think we all have to acknowledge that we will all accidentally drop that Halloween candy wrapper out in the street, or there will always sort of be some kind of leakage or loss to the environment. And so I think we're going to always need things to capture the trash in the environment. And really you want to do that as close to the place and time of leakage as possible. So rather than trying to go clean up the Great Pacific Garbage Patch, we could invest in things like Mr. Trash Wheel here, who is a very charismatic trash collector in Baltimore Harbor, who has his own Twitter feed. You can see these are just some floating booms that collect trash as it comes down the river and then go up a conveyor belt. This is actually from Wanda, Mr. Trash Wheel's sister in Panama. But you can see all this trash coming up, and then it actually goes into, on a solar powered conveyor belt, into a dumpster, which is not shown here. There are also things like stormwater drains, and you can put even finer mesh below those drains to capture smaller items like cigarette butts, for example, or we could all put a filter on our washing machine to capture those textile fibers in the effluent. And then lastly, I think all of us, anywhere, anytime, can pick up litter. Litter generated, in Madison, Wisconsin, can certainly end up in the ocean eventually. So it is worthwhile picking up litter, not just on the beach, not just on the riverfront or in the harbor, but on the street, or really wherever you spend your time. Okay, so lastly, how do we begin to prioritize all these actions that I'm arguing we all have to do simultaneously? And I think this is where the sort of creativity comes in. We can prioritize specific materials or items that are likely to cause the greatest harm. An example of that is a 6-pack ring that could entangle a marine animal, or derelict fishing gear that we know entangles animals. We could prioritize specific items or uses that are easy to eliminate. That's sort of the low-hanging fruit. And the great example of that was banning microbeads and wash-off cosmetics. And we can prioritize actions that can be accomplished immediately, like those filters on washing machines or improving recycling collection. And I think we can and should do all of these, but still simultaneously invest in the more difficult and the longer term and the sustainable solutions, largely around that material, product design, and waste processing that will ultimately lead us towards a zero waste, more circular economy. And just to leave you with some hope, if you didn't know, in March, there was an international agreement that internationally, nations around the world committed to developing a legally binding agreement to address plastic pollution, including in the marine environment. And the first meeting of that intergovernmental negotiating committee will be taking place at the end of this month in Uruguay. So this is something that's being taken seriously, really, at all levels, from municipalities all the way up to the international stage. And I take a lot of optimism from that. So I have to just finish with acknowledging my my colleagues that have contributed to much of this work, and much I didn't have a chance to talk about, especially the more than 10,000 sea semester students that collected all those bits of plastic from plankton nets over the decades, as well as my colleagues at SEA. And then the members of those working groups that George mentioned in the very beginning, which really expanded my knowledge on plastics as a material in the environment, their impacts. I've had the great fortune of working with people from so many different fields, and that's really enriched my view of what you've heard today. And then finally, of course, all of this wouldn't be possible without the support of both government agencies like NSF and the NOAA Marine Debris Program, as well as support from Ocean Conservancy, the March Marine Initiative, and the Richard Lounsbury Foundation. And if you're interested in learning more about SEA, I'll just leave it with this. We just launched, with the help of 3 amazing interns, a website on our SEA Plastics Lab work, and you can visit that here. So with that, I think I will leave that up for a few minutes, but then turn it back over to George. Thank you.
Well, thank you, Kira, for the great talk, and I think we'll be glad to answer any questions. If you have questions, you can please go ahead and put them in the chat. Maybe I'll start with one question. One of the issues that we're seeing is plastic packaging is designed to be really lightweight and have really a high degree of functionality. Unfortunately, that makes it more difficult to recycle, and those technologies aren't yet commercial to recycle that more complex multi-layer plastic packaging material. Now, some of the plastic converters are saying make all your material from recyclable, and that requires you to make thicker plastics and more plastic material, and but then it's more recyclable. So I think that sometimes there's a conflict between that number 1 goal and number 2 goal, and I don't know what you'd say to those plastic converters that we say. Do you focus on recyclability or using less plastic?
This is why this is such a hard problem, because there are very real applications of plastics that we simply can't just stop using plastics in food packaging, for example, right? Or in the medical field. And so there's going to be this push and pull of, is it just the amount of plastics on the planet that matters? No, it's how we use them. So I would argue that really for any application, we have to look at that really closely and say, what are we trying to achieve? What is the best material? And if that best material is plastic, then let's make it out of a plastic that we have a way to recycle at the end of its life. So for food packaging, perhaps that is a place where a biodegradable product is useful if we can build out industrial composting infrastructure. Not that you throw it out your car window and assume that the cucumber wrapper is going to disappear, but is food packaging a place where we could develop a biodegradable material that makes sense and that can work within sort of our societal system? I think an example of where sort of the thicker plastics backfired was in, a lot of these local ordinances that banned single-use plastic bags of a certain thickness, intending to sort of inspire people to use thicker bags. And instead we find very slightly thicker bags that people are still using as single-use plastics. And now we just have more of that material out there to manage. So I fully acknowledge that sort of push and pull. And I think this is why it's such a challenge. We haven't come up with the silver bullet solution for packaging, because it really depends on what the packaging is used for and what our options are and whether we have a material that works or if we have to develop one that would be better.
Thank you. So there's another question from Connor Carlin that says, are you available, interested to speak at plastic industries events?
Yes, thank you. Yeah, and let me just say, I didn't talk a whole lot about industry, but I think industry is, and especially when I talked about solutions, industry has to be part of this conversation, right? And all industries, from the people who are producing the resin, producing the product, producing the packaging, and dealing with the waste. We all have to be in the room together. So absolutely, yes.
Thank you. And another question from an anonymous attendee. It says, is glass a better packaging option? I've heard that many municipalities have prohibited curbside pickup of glass and that broken glass can contaminate recyclable materials and therefore send that contaminated paper, cardboard, and aluminum to the landfill.
Yeah, so that's a really great question because it gets at the very practicality of recycling and single stream recycling. And so I do try to follow along with some of those conversations of people who are in the sort of recycling business. And I've read articles about communities that have prohibited glass. In my community, we still collect glass, but I actually think it gets ground up and used as landfill cover. So is that really recycling anyway? And glass has its own issues being a very heavy material. So yes, I think there are people who are considering, separating streams back out again, moving away from having all the different recyclable materials in a single stream, which of course creates issues of having to separate them and issues of contamination. So I think glass has its issues just like plastics do. The one other thing about glass, though, is if you leave it on the street, it's not going to break down into microplastics with chemical additives.
Thanks. So Jennifer Gottwald asked the question, are there examples of what C students do to affect this issue in their lives and career?
I'm sorry, could you say that one more time? I was looking at the questions on the side.
No problem. Are there examples of what C students do to affect this issue in their lives and career?
Oh my gosh, you need to write our alumni coordinator, because that is exactly what I want to know more about from our alums. We have so many amazing alums who are doing amazing work in all parts of life. I can tell you Carly Herring, who was a student of mine, who actually sailed from Hawaii to San Francisco through the garbage patch, is on the NOAA Marine Debris Program science team. She works with the chief scientist there. So she is directly working with people, distributing funding to prevent marine debris, clean up, and do research. But yes, I am sure the SEA students are doing amazing things. In my time at SEA, and I actually started off as a teaching faculty on ships, which I don't do anymore, but I still interact with our students. And I feel like the students who come to us to learn about the problem, to see it firsthand, to know what it's like to pick out plastic from a plankton net, but to use all that information to go out and make change and do good in the world. So I expect to see great things out of our alums, especially from the past, 5 or 10 years, as we've they've really come in with a solid knowledge about plastics. They're leaving us with experience having seen it and handled them, and an idea of, hopefully great creativity about how to solve the problem.
Excellent. I have one more question. How much of the plastics in the ocean comes from roadside tires versus fibers that come from clothing?
Yeah, thanks for that question. I didn't really have a chance to talk about sort of how we know how much is out there and where it's coming from. So there isn't a great answer. There's been a lot of sort of back of the envelope type calculations to try to estimate, the mass of microfibers in the ocean or the mass of tire wear particles. So there is one study that was out of SFEI, the San Francisco Estuary Institute, where they actually collected water samples coming out of stormwater drains, from wastewater outflow, and then in the San Francisco Bay, surface water and sediments. And what they found was that I think certainly the majority of particles coming out of the stormwater runoff were likely from tire wear. So if now that makes sense because it's actually directly coming, runoff coming off the road. In terms of how that translates into what's actually in San Francisco Bay compared to other sources, things like atmospheric deposition of microfibers, for example, or the breakdown of all those plastic forks over time that are now microplastics, either floating or sitting in the sediment. We don't have a great idea of that. And part of that is the complexity of the marine environment or the, a freshwater environment. Not all plastics float. So when we go out and we measure things in our plankton nets, we're not collecting PVC for the most part. That's all sinking, right? Unless you have sort of a bottle that has air in it or something like that. So in terms of sort of inventories of where it's coming from and where it's ending up, that's still really sort of ballparky estimates.
Well, thank you. Maybe we'll ask one more questions, and Connor Carlin wants me to say what an incredible and great presentation you gave. So I'm supposed to make sure I say that. And then the last question maybe comes from Ho Chin Lee, because we're a little after 4 o'clock. He says, "Thank you for your talk. I'm wondering if there is any activity collecting, sorting, and recycling the ocean plastic."
Oh, that's a really good question. So it's actually not that easy to go out and get plastic from the ocean. I mean, we have this beautiful tall sailing ship behind me, and we tow plankton nets, and typically what you get from a single plankton net fits in the palm of your hand. So it's not a lot of massive plastics. But there are people who are cleaning up beaches and collecting what they call ocean-bound plastic, or even plastic from streets, right? Because sort of everything drains to the ocean eventually. So ocean-bound plastics is a term that you'll hear, where groups will either pay people or somehow source plastic that's been in the environment and then recycle it to the best that they can. It's challenging. These plastics, once they've been in the environment, can be extremely contaminated with chemicals that were already in the environment. They can be dirty, covered in organics. So it's quite a lot of work to actually get to be able to turn them into something new. But you will find products made from ocean plastics. Definitely try to trace your source if you're looking to spend your hard-earned money on these things. But there definitely are groups who collect fishing nets, for example. Like my doormat outside my door is made from reused, fishing line and things like that. So there are definitely plenty of people out there trying to do that. I would just say approach with caution, because some people, greenwashing is a real thing in lots of different ways.
Well, thank you for your talk, Dr. Law. I think, we're sorry we can't be together to, clap, but, you can imagine a lot of people clapping for you right now. So excellent talk and a very interesting presentation.
Great. Well, thank you so much. Thanks for the great questions. It was a pleasure being with you. And yes, hopefully next time in Madison. Have a great day.